presentation of Professor Prasen Chakrabarty. He's the Vice Provost of one of the big public universities in Eastern India. It's ITM. He's a great scientist, a brilliant mind, and he has devoted his career into understanding the artificial intelligence, computer science and engineering, and making that through the interface of our AI with neuroscience, with technology, with whatever, which is good, all right?
I'll just touch upon the research areas that we are actually doing and how AI can be actually implemented. First thing is basically, see, that whenever we used to integrate your AI or machine learning with your neuroscience, first of all, we have to think ourselves that what is basically the goal. That means we have to be very clear about the memory storage and retrieval. For the research scholars, I think some of you are participants, please note down the main salient points of my this talk. Later on, we'll be in touch. And another thing is that you know that there are various areas in your brain. So how the information is transmitted and what is the corresponding neural code. So that is also very important. Another thing is that AI has a huge application in your computational psychiatry. So whenever your ML or AI we have to use, first of all, we have to identify that what are the patterns, that means the electrophysiological pattern, and then we have to apply that for the diagnosis of various neuropsychiatric conditions like either your depression, autism. So these thought disorders, these we have to quantify. And that is the most challenging and very, very difficult task. Why? Because here the prediction is almost, it is means very, very hard to achieve because it is a stochastic phenomenon. How we can actually apply this AI in computational, one thing I'm telling you that we can use some analysis of your suppose multimodal data. And for that, some clinical diagnosis means we have to do. And then from there, we have to discover certain patterns and those individual biomarkers for treatment selection. And after that, we have to actually quantify the treatment, your response with respect to time. Because whenever with respect to time, it is a function of time, then obviously we can apply our various models like the Dopp-Cobbler's model and exponential growth model, and we have to see that what is the trend. So all the participants, the first actual implication is on computational psychiatry. Second thing is that what myself and Dr. Nami...
Professor Prasen, you just mentioned the keyword computational psychiatry. Can you a little bit more elaborate on what the concept is all about? What is computational psychiatry?
Yes. Here what happens that whenever there is a psychiatric disorder, that means there is your certain memory loss also, and that can be quantified using your short-term memory loss and long-term memory loss. So that period that you have to analyze. And there the keywords are basically what? Your event analysis based on two techniques. One is your recall after equidistant timing instant, and another one is non-equidistant timing instant. And there you can use the interpolation technique. So here the quantification of the thought disorders, that is very important. And then your corresponding your AI and ML algorithms that should be trained, that actually identify the corresponding patterns for your future forecasting. Second thing is that very, very important, that is, it's a very, very difficult research aspect, that is actually the brain science. And there the AI approaches that is there for the mainly the neural circuit modulation. That means there what happens? Suppose there is, you have to find out clear-cut your relationship between what? First your neuron, and then the neural activity and behavior. And therein lies the data set, the sample size. So there we can apply the machine learning classifiers, and then we have to find out the accuracy, sensitivity, and specificity. And based on the accuracy estimate, we have to find out that in which nervous system dynamics we can actually include your central or peripheral or your closed loop or your semi-loop. So that is a very, very important, that the neural circuit modulation, how we can do. And in this case, a very, very difficult task is that there are scales. That means the scaling you have to do for the decoding and the modulating of a given human behavior. So in the brain behavior, the temporal and the spatial scales, how you will do that? So that is also another important task, because here there is no statistical trend analysis or supervised. Here, based on your unsupervised stochastic domain, you have to find out that which one the level of resolution, and accordingly how you can map with a particular behavior. Now, in very rare cases, the brain behavior that actually acts as one of the instances that was previously noticed. In that case, it is fine. Otherwise, the approximation theory that we have to apply, and that is the case that we actually, the neuromedicine, that means here comes the term, that means how the various aspects, how the stochastic modeling and the curve fitting, that is most important. Because in curve fitting, what happens in future timing instant, the prediction with respect to time, that is there. Another thing is that here, sometimes you researchers, those who are actually from this AI background, you can understand that dealing with data is very fine, that you will train your data set and accordingly you will use certain tools. But how you can deal with the missing data? Because whenever there is a noise or some skews or some glitches, then how to compute those noise in order to get a response that is actually expected. And that expected and actual, that is the variance. And therein lies the computational technique of fault tolerance. That means there is a bias is set, and up to what time, up to what level, even though there is a deviation, but still it is acceptable or not. So this is a very, very important aspect. Another very important thing is that in all of you, you know, it is very common that just schizophrenic patients. Okay, so the schizophrenia disorders, they are also AI and your neural modeling plays a very, very important role. That means what are the significant parameters, what are the non-significant parameters, and how, first of all, we have to take into consideration into our ML system, into our neural network, that okay, all the parameters that are actually there, we have to take that. After that, make it selected, that means projected. That means only those significant parameters that we can use, and accordingly you have to find out that yes, what are the predominant factors, and then on the basis of your analysis, we can find out that yes, in futuristic timing instant, how the thought disorders of schizophrenic patients that can be regulated. Another thing in our neuro labs international, one very, very important research is going on along with Dr. Nami. That is also very, very difficult topic. That is basically the dementia and Alzheimer's disease. There, how we can apply the stochastic modeling. So there, here, your brain signals play a very, very important role in case of your dementia. That means here we can apply your AI or ML, and in order to assess the dementia risk, because see, if the risk assessment plays a very, very pivotal role, and once we assess the risk, then what will happen? It will automatically enhance the effectiveness of your depression treatments. Both are actually interrelated. So this computational function, that is very, very means important. So here, the EEG signals, and we can use the brain imaging technique. So those signals, when we can actually study, then accordingly some pulses will be generated. And those pulses when generated, from there, we can actually correlate with the dementia signals. And then we have to give some conclusion. Okay, fine. That means what is the loss of your image, your information.
Professor Prosson, can I just interrupt you for a second? So some of the audience, they have a concern that, I've been working with you, so I'm totally familiar with how energetic, fast, and full of energy. You're just shooting the words out of your brilliant mind. I know that. So you're bomb information. I know about this, but some other people find it hard to catch up with you. So is it possible you slow down a little bit, just to let the other people have a better grasp on what you're saying? Just as a note. Yes. Thank you so much.
Okay, thank you. Fine. Okay, fine. So I am just in. I am not going into so much technical in that case. So just I'm telling you that suppose that the mental disorders of a particular patient. That means those disorders we have to analyze, and then while analyzing that, that means that is basically some instances are there. Now, suppose a particular, everything has a basically consequence. That means one is the your premise, another one is the conclusion. That means when you know that, okay, fine, this is the your antecedent and the related consequent is this, then it is fine. That means one-to-one mapping. And then we can understand if this occurs, then accordingly from this particular disorder, this outcome will come. But sometimes what happens that the outcome that is basically that has happened, that is not already noted or observed. In that case, what will happen? The inference or the conclusion, that is very difficult to do, because here the exact symptom, it has not appeared. Then what we have to do? In the past, or there we have to fix that up to this there is a particular observation period, and then in that observation period, how much your symptoms are coming, and then which symptom that is already there right now at this timing instant, it is almost similar to that. That means there in your data mining, there the your nearest algorithm and the k-means that we can use the clustering algorithms, and then we have to find out that, okay, fine, this particular stochastic symptom is almost similar. Here the maximum likelihood measure we have to use. So the maximum likelihood measure from this for this stochastic symptom with respect to the previous symptom is almost similar. So this will be the approximate fine. So since this is basically a stochastic, for that reason, here the AI and ML, the accuracy and also the your forecasting, that plays a very, very important role. And finally, I'll touch upon another thing is that the quantification of human consciousness, that also we can do using your artificial intelligence. And there what will happen, that some means the factors. That means what? That means suppose a wakefulness, that is one thing, awareness is one thing, another is the states. That means at various timing instants, or actually the behavior that actually changes. So based on that, in a conscious mind, in subconscious mind, what are the events going on? What are the behaviors? What are the your practical aspects? And accordingly, we have to make some modeling, and then in there, what will happen? The normal features that will be acted as your input parameters of the neural model. Now, suppose we want to change the in the middle layer, the hidden, or rather the hidden layers, the number of nodes we can change in order to find out the final computational your value. So here the input and output, that one actually acts as a particular means your trend analysis, and that trend analysis will be used for the supervised machine learning concept for the next dataset training. So in this way, the quantification of consciousness also can be measured. So in neuroscience, has a two section. If time permits, later on, we have also worked on the modeling and the forecasting of the thought disorders of patients who have actually suffered from brain cancer. So these are certain thoughts, Dr. Nami, that quantification and how we can do that. Thank you.
Yes, Prasen. Yeah, thank you so much. I mean, it's been, I've been working with you for years, and I know. Yeah, I've been working with you for years.
Next time, I'll keep in mind the level.
Sure. No, this is absolutely great, and I've been working with you, as I was saying, for years, and I know how diverse you think about cross-connecting, computational biology, computational neuroscience to medicine, and you were just making a very good portrayal of what we've been doing. And as you were talking, I was just pulling up some of the works that we published together, just to have an idea, just to share an idea with the excellent participants here. And I put in the chat box some of the the link of some of the papers that I was fortunate to be working with Professor Prasen and his excellent team in India and beyond. So he is always willing to come up with actionable ideas to put that into research protocols. So he's a gem of person, and I'm very happy to have him here as your host of the NeuroGrant Round One here today.